What is the main motivation behind the proposed method in the paper?
The main motivation behind the proposed method in the paper is to develop a novel approach called Representation Finetuning, ReFT, that focuses on intervening on model representations rather than adapting model weights. This approach is inspired by the idea that representations in pre-trained language models, LMs, encode rich semantic information. The paper aims to explore the hypothesis that editing representations directly may be a more powerful alternative to traditional weight-based fine-tuning methods. By training interventions that manipulate a small fraction of model representations, the ReFT methods aim to steer model behaviors to effectively solve downstream tasks at inference time. This approach is seen as a more efficient and effective alternative to weight-based parameter-efficient fine-tuning (PEFT) methods, as it leverages the semantic richness encoded in representations induced by pre-trained LMs.
How does representation fine-tuning, ReFT, differ from traditional weight-based parameter-efficient fine-tuning methods?
Representation fine-tuning, ReFT, differs from traditional weight-based parameter-efficient fine-tuning methods in that ReFT methods train interventions that manipulate a small fraction of model representations instead of adapting model weights. ReFT methods focus on steering model behaviors by intervening on representations to solve downstream tasks at inference time. This approach is inspired by recent work in LM interpretability that shows interventions on representations can lead to faithful causal mechanisms and steer model behaviors effectively. In contrast, traditional weight-based parameter-efficient fine-tuning methods, such as adapters, involve training additional modules on top of the frozen pre-trained model, which can add complexity and inference burden. ReFT methods, like Low-rank Linear Subspace ReFT, LoReFT, intervene on hidden representations in a linear subspace spanned by a low-rank projection matrix, allowing for efficient and effective modifications to model behaviors without the need for extensive weight updates. Overall, ReFT methods offer a more efficient and powerful alternative to weight-based parameter-efficient fine-tuning by focusing on manipulating representations rather than modifying weights directly.
What is the specific method proposed in the paper for representation intervention?
The specific method proposed in the paper for representation intervention is called Representation Finetuning, ReFT. ReFT methods train interventions that manipulate a small fraction of model representations in order to steer model behaviors to solve downstream tasks at inference time. These interventions are drop-in replacements for weight-based parameter-efficient fine-tuning, PEFT methods. The paper focuses on a specific instance of the ReFT family called Low-rank Linear Subspace ReFT, LoReFT, which intervenes on hidden representations in the linear subspace spanned by a low-rank projection matrix. LoReFT edits the representation in the subspace spanned by the columns of the low-rank matrix to take on specific values obtained from a linear projection. The learned parameters of LoReFT include the low-rank matrix, a linear projection matrix, and a bias vector. This method allows for controlling model generations via interventions on representations, providing a more efficient and effective alternative to weight-based PEFTs.
How does low-rank linear subspace ReFT, LoReFT, differ from LoRa in terms of parameter efficiency and performance?
Low-rank linear subspace ReFT, LoReFT, differs from LoRa in terms of parameter efficiency and performance by using 10 times 50 times fewer parameters while achieving state-of-the-art performance for X out of Y number datasets. This difference in parameter efficiency is significant as LoReFT achieves similar or better performance compared to LoRa with a much smaller number of parameters. Additionally, LoReFT outperforms LoRa in certain tasks, showcasing its effectiveness in improving model performance while being more parameter efficient. This indicates that LoReFT is a more efficient and effective alternative to weight-based PEFTs like LoRa, demonstrating its superiority in terms of both parameter efficiency and performance.
Can you explain the key differences between series adapters and parallel adapters in the context of parameter-efficient fine-tuning methods?
Series adapters and parallel adapters are two types of parameter-efficient fine-tuning methods that aim to adapt pre-trained language models to new tasks while minimizing the number of trainable parameters. Series adapters insert components between LM attention or MLP layers, while parallel adapters add modules alongside existing components. The key difference between series adapters and parallel adapters lies in how they integrate additional modules into the model architecture. Series adapters introduce components sequentially in the model's architecture, which means that the output of one adapter becomes the input to the next adapter in a series. On the other hand, parallel adapters add modules alongside existing components without sequential dependencies, allowing for more flexibility in the adaptation process. This difference in integration can impact the complexity and performance of the adaptation process, with series adapters potentially imposing a more structured adaptation flow compared to the more flexible parallel adapters.
What are the key findings of the experiments conducted in the paper on LoReFT performance compared to existing PEFTs on standard benchmarks?
The key findings of the experiments conducted in the paper on LoReFT performance compared to existing PEFTs on standard benchmarks are as follows. 1. LoReFT outperforms all other methods by a considerable margin on common-sense reasoning tasks, setting state-of-the-art performance. 2. In arithmetic reasoning tasks, LoReFT does not perform as well as LoRa and adapters but outperforms prefix tuning. 3. LoReFT achieves a win rate within 1% of GPT-3. 5. Turbo 1106 on instruction following tasks when matched in parameter count to the previous most parameter-efficient PEFT, read. 4. Even after having the parameter count, or using only 1/64th th of the data, LoReFT still outperforms other fine-tuning methods on instruction-following tasks. 5. In natural language understanding tasks on the GLUE benchmark, LoReFT obtains comparable performance with PEFT methods on both model sizes when parameter matched with RED, the previous most parameter-efficient PEFT for this task. Overall, the experiments demonstrate that LoReFT is a highly effective and efficient method for adapting language models to downstream tasks, showing promising results across a variety of benchmarks and outperforming existing PEFT methods in certain scenarios.
How does the paper address the issue of hyperparameter tuning in the context of LoReFT interventions?
The paper addresses the issue of hyperparameter tuning in the context of LoReFT interventions by proposing a specific approach. It suggests learning interventions on a fixed number of prefix and suffix positions in the prompt and tuning 4 hyperparameters: the number of prefix positions to intervene on, the number of suffix positions to intervene on, which set of layers to intervene on, and whether or not to tie intervention parameters across different positions in the same layer. By defining untied and tied variants of LoReFT interventions, the paper simplifies the hyperparameter search space and ensures a fixed additional inference cost that does not scale with prompt length. Additionally, the paper conducts hyperparameter tuning on development sets rather than test sets to avoid overfitting and test the robustness of the settings across different domains. The hyperparameter settings are based on the model that performs best on a development set, with adjustments made for different training set sizes. This approach allows for effective tuning of hyperparameters while maintaining consistency and avoiding direct optimization on test sets.
What are the specific datasets and benchmarks used to evaluate LoReFT in the paper?
The specific datasets and benchmarks used to evaluate LoReFT in the paper are as follows. 1. Common Sense Reasoning Benchmark, which includes 8 common sense reasoning datasets such as BoolQ, PIQA, SIQA, HeliSwag, Winogrande, ARC-E, ARC-C, and OBQA. The task involves multiple choice problems. 2. Arithmetic Reasoning Benchmark, which consists of 4 datasets for Math World problems, including AQUA, GSM-8K, MAWPS, and SVAMP. Models need to generate chain of thought before the final answer. 3. Instruction following benchmark, which evaluates whether models can follow human instructions. The training data used is ultrafeedback, and the evaluation dataset is Alpaca Eval v1. 4. Natural Language Understanding Benchmark, which includes 8 datasets from the GLUE benchmark covering tasks such as sentiment analysis and natural language inference. The models are evaluated on sequence classification tasks. These benchmarks cover a wide range of tasks and domains to provide a comprehensive evaluation of LoReFT's performance in various scenarios.
How does the paper demonstrate the effectiveness of LoReFT in instruction following tasks compared to other fine-tuning methods?
The paper demonstrates the effectiveness of LoReFT in instruction following tasks compared to other fine-tuning methods by conducting experiments on the ultrafeedback dataset using Llama 2 7B models. The results show that LoReFT outperforms all reported fine-tuning methods, including full fine-tuning, when matched in parameter count to the previous most parameter-efficient PEFT, RED. Additionally, LoReFT achieves a win rate within 1% of GPT-3. 5 Turbo 1106. Even after having the parameter count or using only 1/64th th of the data, LoReFT still outperforms other fine-tuning methods. This indicates that LoReFT is highly effective in instruction following tasks, showcasing its superiority over existing fine-tuning methods in terms of performance and efficiency. The experiments highlight the robustness and adaptability of LoReFT in generating responses based on human prompts, making it a promising approach for adapting language models to specific tasks efficiently and effectively.
Can you explain the significance of the PyReFT Python library mentioned in the paper and how it facilitates the adoption of ReFT methods?
The PyReFT Python library mentioned in the paper is significant as it provides a framework for training and sharing representation fine-tuning, ReFT models. This library is built on top of Python, enabling interventions on PyTorch models. It simplifies the process of adopting ReFT methods by offering a user-friendly interface for training ReFT models. With PyReFT, pre-trained language models available on Hugging Face can be easily fine-tuned using ReFT methods. Additionally, the library allows for the seamless sharing of fine-tuned models on Hugging Face's platform. This facilitates the adoption of ReFT methods by providing a standardized and accessible tool for researchers and practitioners to experiment with and apply representation editing techniques to improve model performance. Overall, PyReFT plays a crucial role in lowering the barrier to entry for utilizing ReFT methods, making them more accessible and easier to implement in various natural language processing tasks.